Physics Part 49. Identify the quantity you want to know and then make a list of the quantities you know already. This should make it obvious which equation to be used. Free fall acceleration. Well, a very common example of uniformly accelerated motion is when a body falls freely near the Earth's surface. Because of the gravitational attraction of Earth, all objects fall with the same uniform acceleration. This acceleration is called the acceleration of free fall and is represented by the symbol g. It has a value of 9.81 meter per second, seconds power raised to -2, and is directed downwards. For completeness, we ought to qualify this statement by saying that the fall must be in the absence of air resistance, but in most situations this can be assumed to be true. One reason why the acceleration of free fall is important is that it provides the link between the mass m and the weight w of a body. The relationship is w, which is equal to mg, m for mass and g for gravity. We will meet this equation again in our chapter 5. At present you need only remember the relationship. The acceleration of free fall may be determined by an experiment in which the time of the fall t of a body between 2 points at distance s apart is measured. If the body falls from the rest, we can use the second of the equations for the uniformly accelerated motion in the form g is equal to 2s divided by t square. To calculate the value of g, note that because the time of the fall is likely to be only a few tenths of a second, precisely timing to 1/100th of a second is required. An experiment involving the switching of light gates by falling objects has been described in chapter. The light gates are connected to an electronic timer. Until the 16th century, the idea of acceleration of falling body was not fully appreciated. It was commonly thought that the heavier bodies fell faster than the light ones. This idea was a consequence of the effect of air resistance on light objects with large surface area, such as feathers. However, Galileo Galilei 1564 to 1642 suggested that in the absence of the resistance, all bodies would fall with the same constant acceleration. He showed mathematically that for a body falling from rest, the distance traveled is proportional to the square of the time. Galileo tested the relation experimentally by timing the fall of objects from various levels of the Leaning Tower of Pisa. This is the relation we have derived as S is equal to ut plus half at square. For a body starting from rest, u is equal to 0 and s is equal to half at square. That is, the distance is proportional to time squared. We have mentioned that in most situations air resistance can be neglected. In fact, there are some applications in which this resistance is most important. One is the case of the fall of parachutist, where air resistance is most important. One is the case of the fall of the parachutist, where the air resistance plays a vital part. The velocity of a body falling through a resistive flood